Hello. In this video, we will cover the second half of the modeling with first order equations video. We'll start off with compound interest. The way that investment growth works is that investments grow at a rate that is proportional to the current size. So this is similar to population growth, and we went through and modeled population growth earlier in an earlier video, and we could go through and use the same model for investments. Okay, and so this is that model. All right, and so what we get here is this is the rate of growth. And it is proportional. Okay, so the proportionality constant in this case is going to be the rate of return or the interest rate. And then this is the current size. This is the current, so debt or investment, right? So both grow at a rate proportional to the current size. And just like we went through and solved the population growth in an earlier video, we can go through and we can solve this model the same way. This is a separable differential equation, so we can move the s and the dt and then integrate both sides. And if you solve, you get s of t equals s naught e to the rt, and s of 0 equals s naught. Okay, so just to kind of give you a little bit of background on why this works or how does it make sense, if you think about the way that investments work, right? So if you have $1 million that you invest, and your investment return is 10%, then you would take your $1 million and you'd multiply by 10%. So you get 100,000 from that. And then that's your return. So you would add that to your $1 million. So that's going to be the 100,000 that you get is the change in the size of your investment. And so then your new size is going to be 1.1 million. And so you can see that that is how this model works here. So the DSDT is it's the rate of growth. It's the change in the size of your current portfolio. Okay, so we could think of a derivative as a rate of change. Okay, and so the rate of change of your investment is going to be the 100,000. It's the incremental growth that you'd get. Okay, it's not the $1 million. It's the change in the size of your investment. So yes, you take your $1 million, you'd multiply by your interest rate, which is 10%. That would get you 100,000, and then that's the change in the size. And then you take that 100,000 and you'd add it on to your current debt or investment to get 1.1 million, and then that would be the new size for the next investment period. And then you would take 1.1 million and you would multiply by 10%, and then that would be the change in your investment, and then the result of that would be added to the 1.1 million that you currently have. And then you just keep doing that and doing that and doing that, and you get these compounding returns. And that's the reason we have this compound in compound interest is that your investment compounds by the return ends up growing itself as you go from one time period to the next, right? So if you start off with $1 million and then you get 100,000 and then you add that 100,000, then at the next period, the 100,000 ends up getting you a return. And so that's a compounding of your return. Okay. And so that's explains the basic reasoning behind the model. Why does this work? Why does it go through and model investment growth? And then the solution ends up, looking like this. So this is the equation that actually causes that to happen, causes that behavior to happen. It's an exponential function ends up working, for that model. And so if you then just take your initial investment and put it here, so if you are starting with $1 million, if you put $1 million here and you put your interest rate 10% here, then you can plug in t values and it will produce the outcomes that we just described. It will produce 1.1 million after one time period. After additional time periods, it will produce, continued compounded returns. Okay, so that is the simple basic model that we can use as a starting point for calculating the size of investments. So all of this is going to be our basic model. Okay, so what we want to do now is we want to go through and introduce an additional factor to make this a little bit more complicated. Now, what if we added additional deposits or withdrawals? How does that change the model? All right, so if we start off, our base model is just to take the interest rate and multiply it by the current size, and that gets you the change in the size of your investment. Then the way that we introduce an additional deposit or a withdrawal would be to add another number into that. Okay, so in this case, if we wanted to use the initial example that we described, so if you have $1 million and you're investing it at 10% interest, but then you go through, and each time period, you were to add an additional 20,000 in savings, then the way that would work is you'd have your, this is your current size. So you have $1 million, you have your 10% interest, and then the plus K would be the plus 20,000, and then that would get you the change in the size of your investment. Okay, so let's just kind of walk through that, right? So if you want to calculate what the change is, so again, this is the change in size to your investment. All right, then the way that you'd calculate that change is you'd calculate the current amount, you'd multiply by the interest rate or the return rate, and that's going to get you the number from the previous example, right? That's going to get you the 100,000. So you've got $1 million times 10%, that's 100,000. So the change in your investment is going to be 100,000, and then this adds the additional deposit. So if we're adding an extra 20,000, then you want to add 20,000 to the 100,000, right? So this is going to be 1 million times 10%, that's 100,000, and then we're adding an additional 20,000. So we take 100,000 plus 20,000. So this is the additional deposit / withdrawal. So it could also be a withdrawal, so it could be negative. So if we wanted to go through and say, all right, so let's say you're withdrawing $50,000 per time period. So just to give you for instance for this, what could that possibly model? So $1 million might seem like a lot of money, but if we were modeling retirement, it would not necessarily be a lot. So if you were modeling someone who's 65, they've spent their whole life saving, so they have $1 million as their starting point. So they're going to have, for their first time period, they're going to have $1 million times 10%. So they get 10% is a really good interest rate, but they get $100,000 return, and then they've got to withdraw their living expenses because they're retired. So the K in this case would be negative 50,000. So yes, their $1 million produces $100,000 return, but then they subtract 50,000 from that because they are taking money out, and so their growth rate would not be 100,000; it would only be 50. Right? Okay. And so anyway, so this could go through and model a more complicated situation where we have additional deposits slash withdrawals. All right, so let's say we wanted to go through and solve this. To solve this differential equation, what we can do is we can recall from an earlier video that if we have dy dt equals ay minus b, then this produces y equals b over a plus c e to the at as the return to the as a result for the differential equation. Okay, and so we can use that fact on this, right? So if you just kind of go through and match these up, if we have ds dt equals rs plus k, okay, then in that case we have a is r and b is going to be negative k. B is going to be negative k, so we'll have s equals negative k over r plus c e to the rt. And then if we wanted to go through and solve for c, we can also use the fact that, although it's not written here, that we have s of 0 equals, our initial amount. You can plug in 0, so s of 0 equals negative k over r plus, and then if you put 0 for t here, then the e to the 0 is going to be 1, so we'll have plus c. And so we'll have s naught plus k over r equals c. And then if you just take that and put all of that together, we get s equals negative k over r plus s naught plus k over r e to the rt. And so that produces, that's our solution to the differential equation. That's the solution that would model this scenario where we have both a current amount times an interest rate, and that's going to give us growth, and then we also have additional deposits and withdrawals. So it models the more complicated situation. Now there's something something really cool that you can do with this. If you go through and simplify this a bit, you get a neat result. Let's take a look at that. So we have s of t equals and so what we can do is we can simplify this a bit by multiplying this out. And let's reorder it. And then we can factor out k over r, and we get to here. Now, just recall from the first page, we said s of t equals s naught e to the rt, that this was the return, this was the model without the additional deposits. Okay, so if we have s of t equals this, and this is the return without the additional deposits, so this is return without deposits, that implies that this must be the return from the deposits. And so we can go through, and when we're actually using the model, we can see how much did our investment or debt grow from from the initial amount versus how much did it grow from adding additional deposits or withdrawals. Okay, so with all of that in mind, let's go through and actually try using our model. All right, so let's suppose someone starts saving for retirement at age 25. They save $2,000 per year. Assuming they receive an 8% return. How much will they have? How much will they have saved at age 65? Okay, so we have our model. So S of t equals S naught e to the RT plus K over R e to the RT minus 1. And now we can just take all of this information and just plug into the model. So it doesn't, there's no information in the problem stating the size of their initial investment. So it's implied that the initial investment is 0. And then R is the interest rate. So as a decimal, not this part matters, but because this 0 is going to kill it. But we get 0 times e to the 0.08t. And then K over R. So K, if you recall, so that's the additional deposits. So we have 2,000 the additional deposit per year, divided by the interest rate times e to the interest rate t minus 1. And so this will give us the model. So we get 2,000 over 0.08. That's going to be 25,000 e to the 0.08t minus 1. And so now we can go through and plug in t values, and out will come the size of the investment for that t value after that amount of time. So if we plug in 1 year, we would have the size of the investment after 1 year. And if we plug in 10 years, we'd have the size of the investment after 10 years. So how many years go by from 25 to 65? 40 years. So we want to plug in 40. And so we get 25,000 e to the 0.08 times 40 minus 1. And if you go through and calculate that, it's going to be approximately 588,313. Okay, and so one thing to note, that that sounds like a lot of money, especially when you consider that this person saved $2,000 per year for 40 years. So 2,000 times 40 equals $80,000. They only invested $80,000. Okay. And so if that seems surprising, that's the power of compound returns. So again, compound returns, it's the idea of you getting a return on your return, right? So if you start off and you put $2,000, you save $2,000, and then the first year you get a return of 8%, then on your $2,000, you've made $160 the first year, 2,000 times 8 times 0.08 times 8%. And then the next year, that $160 that you made, you get an 8% return on that. And then the next year, you get an 8% return, an 8% return. And so just each additional time period, the incremental increase in the amount of money that you saved also generates a return. And so you get, that's the notion of compounding returns, where your returns also generate returns. And it's an extremely powerful when it comes to calculating investment returns, is that notion of compounding of returns. Okay, so let's go through a couple more scenarios, because this is kind of, once you've generated this model, it's a fun model to go through and play around with. So let's say that this person has a wealthy relative that gifts them $10,000 to kick off their retirement savings. How much of a difference would that make? Okay, and so we take our model, right? So we've got S of t, and so S naught, so now we're going to have an S naught, so we'll have 10,000 e to the 0.08 t plus, and what we said earlier is 2,000 over 0.08 times e to the 0.08 t minus 1. And if we go through, so that's just taking all the information we had previously, right? This was our model, and we just put 10,000 here instead of 0 here. Otherwise, the rest is the same. Okay, so they start with some money. And what happens if you go through and plug in S of 40? Okay, then after 40 years, this, we're going to have 245,325. And then at this does not change, right? So this is the neat thing about the model, is that it splits up the amount of money that you made from your initial investment, and the returns from your additional deposits. And so you can see the relative effect of each. So starting with $10,000, that produced a good amount of return, but nowhere near as much as adding $2,000 per year, right? So the moral of the story, or the thing that you can learn from this example, is that just because your friend maybe starts off with a little bit of money, from a relative, doesn't mean that you can't go through and save, relatively, I mean, it's not real close, but relatively similar amounts by the end, right? So relative to scale, 588 versus 833 are not wildly different. Obviously, there's some difference there, but the person who starts off with a little bit of money, it's not that they're going to have infinite amounts more, as time goes by. You can go through and you can catch up with that with your $2,000 deposits. So and a good question would be, well, the way that you could catch up to that is you could save $2,500 per year. And so you could go through and check, your friend starts with 10,000, but you save an extra 500 per time period. And then you can go and check this and see what happens. and you could go through and close the gap by saving a little bit more per time period. So what other types of changes can we make to the model? So one thing that might seem a little questionable in the model is the interest rate. If you know much about interest rates, you know that 8% is a pretty good return. What if they received 7%? Then you can go through and do the same model. All right, and so we're back to the initial case, not this, not the $10,000 case here. Instead of having $2,000 over 0.08, we'll have 2,000 over 0.07, and we'll have e to the 0.08. Oop, not 8, 7. T minus 1, and then we can go through and if you simplify that, 2,000 over 0.07 is going to be 28,571 approximately. And then we can go through and plug in our 40 years. After 40 years, how much will they have? They'll have 441,269. And so you could see from that, so how can you interpret that result? And that is that 7% instead of 8%, we went from 588,000 down to 441,000. So that's a significant decrease. Interest rate is important. The return that you get is important when it comes to investments. Okay, you could go through and you could model other scenarios, like what if you got a 5% return instead of an 8% return, and you'll see significant decreases in the amount of money that you have. So yes, interest rate matters a great deal. How about time? How important a factor is time? So what if this person, what if they started saving at age 30? Right? In that case, none of the model doesn't change at all. We still have S of t, and we're back to the 8% scenario here. So that's the 25,000 e to the 0.08 t minus 1. And now instead of saving, if they start at age 30 instead of age 25, then they only get 35 years of compounding instead of 40 years of compounding. And let's see what happens. How much does it decrease? Okay, you can pause the video and guess. We get 386,116 approximately. I'm doing a lot of rounding here. There's a lot of decimals. Now take a look at that. Consider that. So you have two people. They both save the same amount of. They both save the same amounts. They both start saving $2,000 per year. One starts at 25, and they have 588,000 at age 65. The other one starts at 30, and they have 386,000. Okay. And from 588 to 386, that is a huge decrease just for starting a few years later. So when it comes to investment, time is actually considered to be the most important factor. Okay. Let's look at one more scenario for this person. How much would they have to save to have $1 million? right, at age 65. Okay, so you can also go through, and this is an equation. So instead of plugging in time values, instead we could plug in, you know, an amount, an investment total that we want to achieve, and then we could solve for time instead. So we could go the other way. And so to go through and calculate that, we could plug in. So we could plug in $1 million. That's how much we want to have. $1 million. All right, and we know that we want to have the amount after 40 years. So we know that T is going to be 40, and then actually let's do this. Let's write the formula first. All right, so we've got S of T equals S naught e to the RT plus K over R times e to the RT minus 1. And what we want to know is we want to know what K needs to be, right? So K is going to end up being our unknown. How much would they have to save, right, per year? You could add that, per year. So K is going to be unknown, and we're going to go ahead and plug in time because we know that we want that have that amount at age 65. So we know that we want to have 40. So we can then put $1 million here. We're saying they start with nothing, so 0 there. We're assuming they still get 8%, so there's that. Not that those matter because the 0 is going to kill that. K is unknown. We're trying to figure out that. Over 0.08, and then, not equals. And then we get e to the 0.08 times 40 minus 1. Okay. So let's go through and see what happens here. So we've got 1 million. This drops away. So we've got K over 0.08. And then we have e to the 3.2 minus 1. You can multiply the 0.08 over, and we'll get 80,000 equals K times e to the 3.2 minus 1. And then you can calculate that with your calculator and divide it over. And what do we get? K is going to be approximately, drum roll, $3,400. So if you wanted to save $1 million, then you should, and you're under age 25 or below, and you can get an 8% return. So 8% return if you're investing your money in the stock market, if you're just putting it into an S&P 500 fund, then 8% return over a lengthy period of time is actually not unachievable. And so you could make the assumption that you'll get an 8% return over the next 40 years. 40 years is a very long time period. And so if you're age 25 or below and you want to have $1 million when you retire, then $3,400 per year, that's about $300 per month. So if you can save $300 per month toward retirement, then you could have $1 million per year, as long as you just maintained that retirement, that savings. Okay. So there's another thing that I wanted to go through and show you that you can do with this model, and that is that you can model, it's not just investments, okay, but you can, or investments with additional deposits, so someone who's young, but you can also do the other side, right? So if you have a family member who's near retirement age and they have some savings and they want to go through and live off of those savings, you can calculate the amount that they'll have in a future, in the future, based upon the current amount that they have and how much they're going to withdraw. And you can calculate how long their savings will last. All right, so let's suppose a person retires at age 65. So we're at retirement now. They have 500,000 in savings. they've been saving for a long time. Let's assume they receive an 8% interest. That is a very high interest rate for someone who's in retirement, because normally they put their money into bonds, which return less than the stock market does. But just for simplicity, let's stick with it. If they withdraw $50,000 per year to live off of, how much will they have at age 75? So 10 years. Okay, so again, you start off with our basic model. S of t equals S naught e to the RT plus K over R e to the RT minus 1. And so now we just plug things into this. So now the initial amount, so they've got 500,000 they're starting with. So we're going to have 500,000 E, and then 0.08 is the interest rate. And then K over R. So they're withdrawing $50,000. So since it's a withdrawal, we want it to be negative. So we're going to have negative 50,000 divided by 0.08, and then E to the 0.8t minus 1. Okay. And then we can go through and plug in 10 years. So after 10 years, they'll have 500,000 e to the 0.08 times 10 minus, and then we can figure this out. This is going to be 625,000 e to the 0.08 times 10 minus 1. And you can plug that into a calculator. And let's see, you're going to have roughly, so 1,112,770 minus 765,963. And if you combine those, you'll have 346,807. And so after 10 years, their initial savings went from 500,000 down to 346,807. And the way that worked out is that their 500,000 actually grew to about $1.1 million over those 10 years. But the reductions in their savings from the withdrawals totaled $765,963. If you effectively compounded those withdrawals, because of the fact that those withdrawals, the effect of those are going to grow over time in terms of their negative impact. Okay, so that's how you would go through and consider, if you take out 50,000 at the beginning of your time period from your initial investment, then effectively that 50,000, the reduction, is going to end up canceling out compounding returns that you would have gotten if you had not deducted it. So that's why this total is more than 500,000, is because it's going through and it's compounding your withdrawals to counteract the effect that you would have gotten if you had not taken that money out. And so when you combine those, your initial investment grows to 1.1 million. Then the negative effect of your withdrawals is 765,000, and so you end up with 346,000. $807 total after 10 years. So that's where they would be at if they started with 500,000. So after 10 years, they will only have deducted $150,000. However, now this is something to consider, and that is that they now their basis is 346,000, and so their return, right? If they're getting 8%, their return is now going to be smaller moving forward. Okay, so um, what does that tell you? So it looks like from 500,000 down to 346,000, it only dropped by 150,000, right? So it looks like they have maybe another 30 or so years that you could get at that rate, right? At that rate. So if you think about it, if you've got 500 and that goes down by 150, then you've got another 150 you could take out 2 more times. However, the problem with that is that this is now the basis for growth moving forward. And so the returns are now going to be smaller as your investment size shrinks. All right. So in terms to answer the question, how long until their savings run out? So based upon the previous route, you might say 30 or so years. Right. If you went from 500 down to 325 after, what was it, 325, 346 after 10 years, then it looks like you're pulling out about 150K per 10 years. And so you might have another 20 or so years left. And so you get 30 years total, but that would not be true. All right, so how long until their savings run out? So again, we want to take the model, and now in this case, so if we start off, you have S of t, S naught, e to the RT, we've got k over r, e to the RT minus 1. And so let's say, so they have 500,000, e to the 0.08t minus 50,000 over 0.08 e to the 0.08 t minus 1. And so if we want to know how long until their savings run out, so we want to know how long until this is 0, right? The S of t is the size of their investment at a given time. And so we want to figure out when would the size be 0. So we want to replace this with 0. And then you'll have 500,000. And then you need to solve for t. So how long will their investment last? Will it last 30 years? I mean, that's what it looks like. And to go through and calculate that, let's actually just go through and multiply this out. So when you calculate that, you're going to get 625,000. And then we can distribute. And so and then you can combine these. Oops, that should be a minus 125,000, not minus 125. And we could combine this. We get 125,000 e to the 0.08 t equals 625,000. And then you can divide. Take the natural log of both sides. Divide again. And what do we get? We get about 20 years. All right, so how can we interpret that compared to our previous result? All right, so if you start off with 500,000, after 10 years, your investment has shrunk to about 350. All right, but now your investment is smaller, and so the return is going to be smaller moving forward. And because of that, from 350 over the next 10 years, you go from 350 to zero if you're taking out $50,000 per year. And so you do not get the rate does not continue at that starting rate. So from 500 down to 350, that minus 150, it doesn't stay at that rate because your investment got smaller. Okay, so that is all of our compound interest. Let's move on to our second topic. Escape velocity. Suppose a mass is projected away from the Earth. All right, ignoring air resistance, but taking gravity into account, find the velocity at any time. Okay. Once we've done that, find the initial velocity required to lift the mass to altitude lift the mass to altitude. Xi above the surface. And then finally, find the velocity required so that the mass does not return to the Earth. All right, so this is called the escape velocity. Okay. Let's draw ourselves a picture and see if we can go through and model this scenario. Right, so we have the Earth. Okay, we have an object, and it is launched upward. So we'll say its height above the surface of the Earth is y. And then let's also extend this line down to the center of the Earth, and we'll say the radius of the Earth is r. So here's our mass, and it's extended upward. and we'll say that this is the height that it is above the ground is distance y, and then the distance to the center of the Earth is r. So this will give us kind of the starting point for a model. All right, so we're supposed to model gravity. How do we model gravity? Okay, so one issue with going through and modeling gravity, so we've modeled gravity in previous videos, and we just went through and said it was negative mg, mass times the acceleration due to gravity. The problem with using that model is that negative mg only works for modeling gravity around the surface of the Earth. As we extend far above the surface of the Earth, that model is not going to be complex enough. So what we need to do is we need to go through and use a more general model for gravity. And so what you can do is you can go through and look up the force due to gravity between two objects. And there's a formula for that. And so it's G m little m over d squared. Okay, and so again, this is the force due to gravity. The gravitational force between two objects. Okay, and then so what we have here is that this is the distance between the objects. We should say the distance between the center of the objects. And then capital G is a gravitational constant. Capital M, we'll say, is the mass for one of the objects. And little m is the mass for the other. And so this formula enables us to go through and find the force due to gravity between any two objects. So this is the force that two objects from gravity exert on each other. Okay. And so we can use this to model gravity not only at the surface of the Earth, but well above the surface of the Earth. Okay. So what we're going to do then is to go through and try and come up with a formula for this. All right, so the formula that we're going to do, so we're going to say the force due to gravity at height y, okay, height y, so the force due to gravity between the object, which we're launching, and the Earth, we're going to create a function for that, a formula for that. Okay, so we're going to take G, which is the gravitational constant, and we're going to take M, which is the mass, we're going to say is the mass of the Earth, and we're going to combine those into a single constant, okay, that we're going to call negative, we're going to call K, okay, and let's leave off the negative for a second. We're going to call that K. So we're going to take these two, combine them, that's going to be K, and then we'll say the mass for our object that we're launching is M, okay, and then the distance between the center of the two objects, right? So if our object is at height y above the Earth, okay, then the distance between our object and the center of the Earth is going to be y, that's the distance to the center, plus r, that's the distance, sorry, the y is the distance to the edge, to the surface, and then r is the distance to the center, and so we need to add the two. And square. And then finally, we're going to apply a directionality to the force, and we're going to say the force is negative, right? That it's acting to pull the object that's going upward, it's acting to pull it toward the set, to pull it downward. And so we're going to say negative is downward in our model. Okay, and so this can go through, and this function, if we plug in y values, it will produce the force between the two objects, right? Between our object that we're launching and the Earth. If we go through and plug f of 0 in, what is f of 0? F of 0 would be the force that we get that's at the surface of the Earth. Well, that force we know is going to be negative mg. So that is the result that we've used previously for modeling forces, and that's the force due to gravity that's on the surface of the Earth. So this gives us a general formula for the force anywhere above, at the surface or above. If we plug in 0, then we end up getting the force that's on the surface of the Earth. Now, the neat thing is you can combine these two to enable you to go through and come up with a value that we can plug in for K, right? So if you take 0 and plug it into this top formula here, we're going to get negative Km divided by 0 plus R squared. And we know that f of 0 from this previous result is negative mg, so we can take negative mg equals negative km over r squared, right? The m's will cancel, and then you could multiply the r squared over, and we get k equals g r squared. And then taking that and plugging it into our initial result, and we can get the force due to gravity at any height y on our object is going to be negative mg r squared over k plus, or y plus r squared. And so that's the way that we can use the universal force formula for due to gravity between two objects to go through and calculate a force function for our object. Okay, so next we can go through and we can use a result that we've used previously in an earlier video is Newton's second law. So Newton's second law tells us that the mass times acceleration of an object is equal to the net force. Well, if the only force that is acting on the object is given by the force due to gravity, then that's going to equal mgr squared over, that's going to equal the result we just got, r plus y squared. Okay, and what did we get? We got that it's negative. Okay, and so you can go through and you can cancel the m's, and so we get dv dt equals gr squared over r plus y squared. Okay. And then v of 0 would equal v naught, right? So our initial velocity for the object would be given by v naught. And so what we've got here is we've been able to construct a differential equation to go through and model, our object, right? The motion of our object. We've got its position, we've got its velocity, we've got time. Now, the issue, if we wanted to go through and solve this differential equation, is that there are too many variables. Okay, so if we have v and t, then we could go through and separate the variables and solve the differential equation. Or if we had a y here, then we could go through and separate the variables and solve the differential equation. However, at the moment, we have 1, 2, 3 variables when we can only solve this with 2. All right, so what we can do is we can go through and use the fact that dv dt equals dv dy times dy dt, which equals dv dy times v, right? And so we can go through and use the fact that you can cancel, right? You've got that algebra of calculus. You can cancel these middle guys to create a new a new result, right? The dv dt is equal to the product of these two. And then we know that the rate of change of y, right, the derivative of y with respect to t, well, that's just the velocity itself. So we can rewrite dv dt as the rate of change of velocity with respect to position instead of with respect to time, and then times the velocity. And then by taking that, we can substitute that in place of dv dt, and you'll end up with dv dy times v equals negative g r squared over r plus y squared. And then at this point, we can go through and separate the variables. All right, so we'll get v dy equals negative g r squared over r plus y squared dy. Oh, that's supposed to be a dv there. Then once you've done that, you can integrate both sides. And here we'll get v squared over 2. And over here, we're going to get gr squared times r plus y to the negative 1 plus c. Okay, and now if we want to go through and solve for c, we can use our initial condition and plug in 0. If you plug in 0, right, for v, then v is going to become, so yes, let's just pause here for a second without rushing into it. So this is a function, right? It's just not modeled that way. This is v of y squared over 2 equals gr squared r plus y to the negative 1 plus c. So here you could plug in y values, and out come your velocity for that y position. So that's a clear thing to understand here, is that this is no longer a function of t, it's a function of y. All right, so if we go through and plug in, you know, when the object is, 1,000 miles above the surface of the Earth, if you plug in 1,000 for y, it will give you the velocity at that position, right? So if we want to go through and solve for c, we need to go through and plug in something for the velocity here. Well, what we've got is we've got here the velocity at time 0, right? Says that when t equals 0, the velocity is equal to v naught, okay, at the initial time. Well, we know the initial time also corresponds to the surface of the Earth, right? So when if the velocity is v naught at launch, at time equals 0, well, at time equals 0, you're also going to be on the surface of the Earth, which is when y equals 0. All right, so we can go through and plug in 0 for y, and that's going to end up getting us v of 0 is going to end up being v naught. It's going to end up being the initial, the velocity when time equals 0 is also going to be the velocity at when y equals 0, when you're on the surface of the Earth. And then from there, you can go through and you can just solve this. Right, so we're going to get gr squared. If you plug in y equals 0, you get r to the negative 1 plus c. And then this cancels one of those. We get v naught squared over 2gr squared equals c. Hold on, that's not right. We get v naught squared over 2 minus g r equals c. And then we can take that and plug that in place of the c, and let's do that on the next page. So we're going to have v naught squared over 2 equals g r squared over r plus y plus v naught squared over 2 minus gr, and then we can multiply through by 2 and take this square root. And let's just do both of those at once. Okay, hold on. This is v of t squared over 2. And then so v of t is going to equal 2gr squared over r plus y plus v naught squared minus 2gr, and then we'll have the square root. Plus and minus. Okay, so and let's just talk about one more thing here. So the plus slash minus is chosen depending upon the scenario. So the scenario would be based upon whether the object is rising or falling. Okay, hold on. One more thing here. These should be y's, not t's. Okay. And so the way that this works, the way that our model works that we ended up with is that you plug in a position and then out comes a velocity. And that velocity could be positive or negative depending upon the scenario that you have for the object. You know, just so, for example, if you plug in v of 0, that would be the velocity on the surface of the Earth, right? That could either be plus, right? You're launching, or it could be minus, right? Which is that the object is falling back to the Earth and you'd want to be finding the velocity when it strikes the Earth. Okay, so that's the plus or minus here, is that for every y value, you're going to end up with 2 possible velocities. One that models the velocity going up, and that's going to be positive, and then 2, negative velocity that models the velocity coming back downward. Okay, so this gives the velocity at any time, and that's how you find it. So that was the first question we were asked to go through and do. All right, so find the velocity required, find the velocity at any time. That was this. Check. All right, find the velocity required to lift the mass to altitude xi above the surface. So that's what we want to do next. So how do we go through and find the velocity required to lift the object to altitude xi? Okay, well, what we're going to do is we're going to use the fact that the max altitude what would the max altitude be? The max altitude is going to be when you run out of velocity, when you hit the maximum, your velocity has just is petering out as you're rising higher and higher and higher above the surface of the Earth, fighting that gravity. And then eventually your object stops rising, right? If you think about it, it's going up, you know, the velocity, the position is rising. So y is increasing, v is decreasing, and then eventually it hits a max point, and then then it starts falling. That's going to be your max altitude. And the velocity is, well, I should clarify it by decreasing. It's positive and decreasing. Velocity is greater than 0, but decreasing. And then finally you get to a max altitude, and then at that point your velocity, you run out of velocity, and then your velocity starts to go negative. Velocity is less than 0, and then you're going to start falling back to the surface, back toward the surface of the Earth. And so what we can do is we can go through and say the max altitude is going to occur where v equals 0. Okay, so you start off, you launch, you've got a positive velocity. As you're launching above the surface of the Earth, your velocity is slowly decreasing, but it's positive. And as you're going upward and upward and upward, eventually you get to the top of, as high as you can go, your max altitude. And at that max altitude is where your velocity is just going to run out of velocity, and then you're going to hit velocity equals 0, and then your velocity is going to turn negative as you start coming back toward the surface of the Earth. And so what we can do is we can plug in v equals 0 to solve for max altitude. All right, so let's do that on the next page. All right, so max altitude. So we're going to set v equal to 0. And we're going to go ahead and we're going to say why the max altitude is going to be given by xi. So we'll have 0 equals plus or minus the square root 2gr squared over r plus xi plus v naught squared minus 2gr. And then you can square both sides. And then we can go through and move these terms to the other side. All right, so you're going to move these over. You're going to divide this over. Oops. You're going to divide this over. Okay, and then we can flip both sides and move the r over. And then we can go through and get common denominators. Oops, made a mistake here. This should be a square. Okay, and then if you simplify that, you'll get xi equals this and this cancel, and we get v naught squared r over 2gr minus v naught squared. And so this formula here is the max altitude for a given initial velocity. equation. So what you can do is plug in initial velocity and out will come the max altitude, right? That's kind of neat. So if you know how much lift you have on your object, like if you have a rocket and you know its initial velocity when it's launched, then you can go through and you can calculate how high that rocket will actually get above the surface of the Earth using that formula. Okay, so that takes care of this. And then the last thing, find the velocity required so that the mass does not return to the Earth. Okay, so in order to go through and do that, what we're going to do is we're going to go through and solve for velocity in this equation. That way we can plug in altitudes and out will come velocities. So let's do that. All right, hold on. All right, so we're going to take this, multiply it over, and let's see what we get. Okay, so what I did there is I took this and I just multiplied it over to the other side, and that way you'll get 2gr xi minus v naught squared xi equals v naught squared r, and that's what we have there. And then at this point, you can get the v naughts on the same side, so you get v naught squared r plus v naught squared xi equals 2g r xi, and v naught squared r plus xi. And then finally, we get v naught equals the square root of 2g r xi over r plus xi. So this gives us a function where we can plug in altitude and output is the velocity required. Okay, so what if we want the altitude to be to have no maximum, right? So you don't return to the Earth. There is no maximum altitude. Then we could model that by going through and finding the limit as xi goes to infinity. And if you go through and take v naught equals the limit as xi goes to infinity, right? So there's no max altitude. Max altitude is infinite. As xi goes to infinity, this r term that's in the denominator is going to become inconsequentially small, and so you effectively can ignore it. The xi's will end up canceling, and you get the square root of 2gr. Okay, so there's your formula. That's the escape velocity. Okay. And so there's your video on the second video on modeling first order equations. So we discussed compound interest and a variety of different scenarios. And then we went through and answered the question of how do you go through and find escape velocity by first modeling velocity at any time, for an object using gravity alone, then using that result to find the velocity required for a given altitude, and then taking that altitude and taking it to infinity. Okay. All right. So that's it. Thank you for watching. See you next time.